In this video today, we'll be doing a fluids exam that I took in my class through chapters 1 through 3. And then I'm just going to show you this. This was given to me in my test. So this has to do with values that we're going to assume for water or different liquids. Yeah, so it says for water in this exam, it gives us the specific weights and densities that we're going to assume. It also gives us what gravity is, and if we need it, the gas constant for dry air. So if I refer to this, that's what that is. For our first question, it says oil with a dynamic viscosity of 1 times 10 to the negative 4 pounds force times seconds per feet squared is used as a lubricant between two parts of a machine that slide past one another with a velocity difference of 4 feet per second. What spacing in inches is required if you do not want a shear stress of more than 2 pounds force per feet squared? So assume coet flow. So with every question we say, what's our goal? Let's see. What spacing in inches is required if you don't want a shear stress? So find spacing. Find spacing in inches. And this variable is going to be the y. Y is distance. I don't know. We're going to use y. We're given that viscosity, dynamic viscosity, that's a bad mu, but whatever, is 1 times 10 to the negative 4. Okay, and then velocity is 4 feet per second. And then shear stress, we don't want it to exceed 2 pounds force. So shear stress, tau, is represented by tau. We don't want it to be more than 2 pounds force per feet squared. And then we need to remember what coet flow is. All it is coet flow is when you have one wall that's moving and one that's not. So let's say that this wall is moving, and then this wall moving causes a flow of water or some liquid. This wall is stationary, this one's moving. When this water is flowing, it will create a linear velocity gradient. So it'll look like this. The velocity will be fastest at the top, but the biggest thing that you need to know in coet flow is that the velocity gradient is linear. All that means is makes this question easier, but also that I'm about to write the formula here. Maybe it'll be easier to explain when we write the formula. So that dynamic viscosity, or the definition of viscosity, is shear stress equals dynamic viscosity, also referred just to as viscosity, of the derivative of velocity with respect to the distance. Y is distance between the walls. So the velocity gradient is this derivative of velocity over with the respective distance. So that's what the velocity gradient is. So now we know it's linear. We don't have to take a derivative. Basically, we just don't have to take a derivative of any crazy functions or anything like that. We know it's linear, so we can go ahead and just plug these numbers in. That's all that means. So let's see. So it gives us mu, right? It gives us that right here. Or I'll look at our givens. It gives us our velocity. It gives us our and it gives us our shear stress that we don't want to exceed. So, and then we want to find our spacing, so we need to find this dy. So, and our change of velocity is just for this dv is just this, because our change in velocity, since it's linear, we can just plug it in as 4 feet per second. So let's rearrange it and solve for dy. So we'll get dy equals and then all of this over shear stress. Right. Yeah, so it's a pretty simple problem, and then you just literally plug in and chug everything we're given. So we get 1 times 10 negative 4. I'm just plugging in what we got from our givens. Yeah, our units cancel. Then we're just left with feet. So we put that in our calculator. We get that it is 2 times 10 to the negative 4 feet of spacing. So that's what the spacing is required if you don't want to shear stress more than of 2 pounds force per feet squared. But it wants to answer in inches, so we got to convert this. We know that to convert from feet to inches, you just multiply by 12, right? So you will get an answer of, and there you go. The next problem in the textbook says a wood block with a specific gravity of 0.4 is 50 centimeters long, and that's the length that will extend into the page that we can't see. We just need to know that to find the volume later. And then it says that it's the wood block is 20 centimeters wide and 7 centimeters thick. If placed in water as shown, how high would the wood block extend above the water line is what we're trying to find. That's represented by H. So our goal is just to find H, right? Just how much higher is the wood block floating above the water line. We're given the specific gravity of the wood block, which is 0.4, and then we're given the length into the page, 0.5 meters, and then we're also given this diagram. So first things first, let's find the density. We're gonna need density to find the mass later, but we don't. I'm just gonna find the density real quick of the wood block, just so we can have it for later. That is a rho symbol, not a P. I'm not very good at drawing them. So this is the density of the wood block is going to be equal to the specific gravity of the wood block multiplied by the density of water at 4 degrees Celsius. Using the given values that were shown in the test, it says for water, assume that water density is 1,000 kilograms per meter cubed. So that's what we're going to use. Alright, and then if you do that, you get 400 kilograms per meter cubed. And that's equal to density. Okay, so the first step, or one of the first steps you want to take to solving a buoyancy force question, which is what this is draw a free body diagram to think of all the forces that are acting here. And we know it's a buoyancy force question because there's a wood block floating, or there's some sort of block, there's some sort of material floating in water, so we know that that is in play. The only forces acting here is the buoyancy force that is holding it up, allowing it to float, and then there is the weight force of the wood block. Using our statics and physics, we know that it's in equilibrium because it's just sitting still there floating. So we know that the forces in the y direction will equal 0. So that means that the buoyancy force will equal the force of weight. So we have this equation here that gives us a little relationship, and we'll be able to use this relationship to find the height. So to do that, we have to remember what the formulas are for these forces. The buoyancy force formula is the specific weight of the liquid it's floating in. In this case, it's water, times the volume of the object that is displaced under the water. So the volume displaced in this case would just be under the water line, right? So the 7 centimeters minus h, right? And then the force of weight equation is mass times gravity, right? Alright, so we got to think about this. We're trying to find h, right? So where does the variable h lie in this? And the answer is the height variable lies within the volume. So we know the volume of a rectangle is length times width times height, right? So there's our height value. The volume displaced, which we need, is, it's a rectangle, is, we know the length, right? It says 50 centimeters, so same thing as half a meter. The width is 20 centimeters, so that's the same thing as 0.2 meters. And then we know, we don't know the height displaced, right? Really, we don't really know that. That's what we're trying to find. But we do know it is 0.07 meters, which is the same as 7 centimeters, minus that h value, right? We know that the amount of the block that's underwater is this value minus h, right? So that's all I did there. And then, so we'll be able to plug that in. So this should be the only, we're only trying to solve for this variable h. So we need to know the specific weight of water, which the test gives us. We know gravity, test also gives us that. We don't know this mass value. So that's why we solve for this density of the wood block, because we need to know the mass of the wood block. So we can use the density formula to find for mass. So remember, the density formula is mass over volume. So we know if we rearrange that, we can say that mass equals density times volume. We know the density, we solve for that. Now we need to know the volume of the wood block. So let's plug in these values, which the volume is just length times width times height, right? Which we know all those. So 400, and then in meters, and then we get a mass. Mass is 2.8 kilograms. Okay, put that in the calculator. That's a 7. So we have everything we need to know to solve for this. So let's go ahead and write it down here. I'm going to rearrange this. So we have equals water. So then we can rewrite this as this equation up here, right? I'm gonna go ahead and multiply these out. So 5 times 2 is 10, but well, yeah, I'm dumb, so I have to put that in the calculator. 0.1. Okay, that makes sense. So 0.1 meters squared. All I did was just multiply these out real quick instead of writing the full length. And then 0.07 meters minus h, the height, equals okay. We can go ahead and multiply this out, and then I'm going to multiply it and add it over, so we get 0.1 meters squared equals mg minus 0.007. Okay. Did some rearranging. And then let's rearrange this again. So, we'll just keep it like this actually. So let's go ahead and plug in all these values and then solve for h here. So we're gonna have to use some unit conversions here later on, but let's go ahead and do this. Equals mass times gravity, so 2.8 kilograms times 9.81. What does the test say? What does the test say for gravity? 9.81 meters per second squared. So it's just the regular. And then specific weight of water is 9.81, right? Is what we said. What does it say in the test? 9.81 kilonewtons. I'm just gonna convert that to newtons real quick. So and then we gotta minus this value. Okay, so let's put that in the calculator real quick. Just so you guys know, we gotta remember that kilograms times the unit kilogram times meters per second squared is equal to 1 Newton. So that's important to remember. So we'll be left. This will just be we'll be left with this meters cubed. So we got 0.0028 meters cubed minus and I forgot a negative sign, huh? Yeah, I've been forgetting a negative sign this whole time. Yeah, I should have brought that negative sign down the whole time. Okay, that makes sense. So if you subtract these and then divide, if you find the difference between these and then divide by this, you will get that H equals 0.042 meters. So that is an answer, but the whole problem's been in centimeters, so we can go ahead and convert that. If you multiply that by 100, you get 4.2 centimeters. So the wood block is floating above the water line by 4.2 centimeters. That's not very. Problem 3 in the test says, what is the specific gravity of the mystery fluid right here? If the pressure is at the bottom of the fluid is 41 kilopascals. What is the gauge pressure at the bottom of the tank right here? And what is the piezometric head at both points A and B? Okay, so let's do this. So goal is to find specific gravity of the mystery fluid. And then it says to find the pressure at the bottom of the tank. Mercury. And then it says to find the piezometric head. Piezometric head. It's gonna be that. That's what it looks like. Okay, so then we're given. Everything we're given is labeled on this diagram that was on my test. So what's going on here is we're going to have to use a hydrostatic equation, but we're not given we're given variables in all different places, right? So let's find the specific gravity first, right? So we gotta label this 1, 2, 3. So we know that using the hydrostatic equation that P1, let's look at it actually. The textbook hydrostatic equation, we use this P1 over specific, P1 plus specific weight times height equals P2 Okay, so we have to find the specific gravity. So we know that specific gravity is equal to right. So we need to find the specific gravity, we have to find the specific weight. So we need to solve for the right. We can do. Oh no, it's already good. So we need to find the specific weight. So let's start filling in what we know on this equation. So we know that this is 0 because we're trying to find the gauge pressure, right? Gauge pressure. So this is it's exposed to the atmosphere, so 0 gauge pressure. We need to know we got to solve for the specific weight, right? I'm gonna put an M here for mystery. I'll put MY so it doesn't get confused with mercury. And then we know Z1 and Z2. If we say that the bottom is Z is 0, so like the very bottom is 0. So let's rearrange this so that we're solving for specific weight. So let's get and then okay, so we know pressure at point 2 is given. We know the difference in height is 4.3 meters between point 1 and point 2. So we can go to fill that in. And then I went ahead and converted it from kilopascals to pascals, which we know a pascal is, so I just multiply by 1,000 to convert it, and then we know a pascal is Newton, same as a Newton per meter squared. And then divided by that. So then we will get that, put that in the calculator. Is equal to 953, and if you round it, put a 5 there, newtons per meter. So that is the specific weight of the mystery fluid. But we need to find the specific gravity. So to do that, we will plug this into this right here. So divide it by 9810. We get that SG is equal to 0.97. So that is the answer for that. Yeah. So that's the specific gravity of mystery fluid. The next question is to find the gauge pressure at the bottom of the tank. Okay, so they give us the specific gravity of the mercury. So let's use the specific gravity of the mercury to find the specific weight of the fluid mercury. So specific weight. So then I'm going to put Hg for mercury. Hg in the periodic table represents mercury, so that's why I did that. We know that the specific gravity is 13.3, and then you're going to multiply it by the temperature of water at 4 degrees Celsius. It's also what the test gives us to assume what the water is. So we get that the specific weight of mercury is, put it in the calculator, 130,473 newtons per meter cubed. Okay, so that'll be useful when we do the hydrostatic equation between point 2 and 3. So we get 0.2 plus, and we're in the liquid mercury right now, equals pressure 3 plus okay, so that's the hydrostatic equation. We're trying to find P3 in this instance, right? The pressure at the bottom. Okay, so let's rearrange this. So we'll get P2 plus okay, so I rearranged it, solve for pressure at the 0.3 at the bottom. So we know the difference in this is 2.5, difference of points between 2 and 3. We know we just solved for this, the specific weight of mercury, and we're given the pressure at 0.2. So let's go ahead and plug this in. I'm going to go ahead and convert this to pascals, and then we know, or to newtons. Yeah, I'm going to convert it to pascals, and then we know that's equal to newton per meter squared. And we add that to specific weight of mercury times the difference in height of the 2 points, which is 2.5 meters, and put that in our calculator. Okay, so that gives us pressure is 36718.2.5 newtons per meter squared. That is also equivalent to 367, and you round it, 0.2 kilopascals. So that is the pressure at the bottom. Okay, so the next question is to find the piezometric head at points A and B, given right here. When the important thing to know about piezometric head is its units as meters, right? But also, piezometric head is going to be the same for B and A. They're in the same liquid, and the textbook says that if they're in the same liquid and the density is uniform, which we're always assuming that in like all of the fluid questions we're doing, we're assuming that the fluid is incompressible, meaning the density is constant throughout the whole liquid. We know that these A and B piezometric head will be the same. So this is the formula of piezometric head. So pressure over a specific weight plus the depth will give you piezometric head. I'll do the piezometric head for both to show that they equal, but if you were taking the test, you would save time by just doing one. So to find the pressure at point A, we need to do the pressure here plus the depth 1.28 down. So I'll show you what that looks like. So we know the pressure here is 4.1. And then you add the depth. Specific weight is specific weight. What did I say that was? 130473. 130473. Okay. And then multiply that by the height. Depth is 2.5 minus 1.28. Okay. I kind of just did the hydrostatic equation again. All I did was to find PA, I took the known pressure at point 2 and then did specific weight times the depth within the liquid of mercury to find the pressure. So if I put that in the calculator, what is that? You get that the pressure is equal to 2000177 pascals or newtons per meter squared. So then plug that into this equation. So you get, this is at point A, equals 2000177. Specific weight of mercury. We're in mercury right now. We do 130473. And then you will add the depth, which the depth of point A is, you will do the entire depth, right? So 4.3 plus 2.5 minus that 1.28. So 4.3, right? Yeah. Can't remember anything. Okay, so that will give us the answer here. You get piezometric pressure of 7.05 meters. So let's do it for the other point, point B. Okay, so same strategy. We gotta find pressure. So pressure at point B equals 41000 PA plus 130473. This is the specific weight of mercury. Multiply it by the depth. 2.5 meters minus 0.38. It's pretty close to the bottom. So that equal to okay. Pressure is higher than this number, which makes sense, right? Because farther around another one, somewhere around this one. Makes sense that that pressure is higher than that. Now we can plug it into the piezometric head for B equation. So you got 317,603, and then we said that 130 specific weight of mercury. And then actually, don't multiply, you add 4.3 meters, then add 2.5, and then subtract 0.38 meters. Let's put this in the calculator, and they should be the same. If they're not the same, they should be at least really close. Just because I had probably some rounding errors or something. And we got okay, last problem on the test. It says a rectangular gate with a width of 0.8 meters is underwater with the parameters as shown. What force F directed straight upwards is required to open the gate? Neglect the weight of the gate. Use SI units. Okay, so the steps with all of these gate problems where you're trying to find out if it's going to open or not is to first find the pressure force from the liquid, locate the center of pressure on the gate, and then take a moment about the hinge. So those are our first three steps. Let's write our goal. Our goal is to find the F value that will allow this gate to be open. And then we're given that the width is 0.8 meters. And that's into the page, so we can't see that on the diagram. And then it says, it says to neglect the weight of the gate. So the only thing acting against this F value that we're going to find is this pressure force, which it won't be acting there. It will be acting more down here. So I'll redraw that. The center of pressure will be lower. Right. Okay, so first up, right, find FP. So we gotta remember what the pressure force formula is, which is it's water, right? Yeah, water. Specific weight of water, which is the liquid, times the depth in relation to the centroid. And then we gotta multiply by the area of the gate. Okay, so the textbook gives us that specific weight of water is 9.80 kilonewtons. Did I say textbook? The test, whatever. That first page. And then we need to know the height, the depth. So the depth will just be, I'll write it out and then explain it. So what I'm doing here is we got to find the height from the surface of the water to the centroid of the gate. So to do that, we know that it's a rectangular gate, right? So the centroid is going to be just split the half, like right in the middle is where the centroid is going to be. So we know it's going to be this 3.4 meters deep, and then we know it's going to be right around this halfway mark. And so we know that this length, we want half of this, right? So to find that X value, I just did 4.5, which is this whole length, minus 3.4, and then we're going to half it because we want that centroid, right? So that's all I did there. And then that will give us a value for the height from the surface of the water, or depth for the surface of the water to the centroid of the gate is 3.95 meters. And then we need to know the area of the gate. It's a rectangular gate, so we just know the area is length times width. So length times width, we know we're given the width, and then the length we're gonna have to find, right? So we're gonna have to do some trigonometry here. I'll draw a triangle. So we got this is the gate. This hypotenuse is the gate, and we need to find the length. Oh gosh, that was bad. We need to find the length of that. We know that from the diagram, we know this angle is 40 degrees. So we can do, oh, 1 second. And we know that this value is 1.1 meters. And again, where I got this value, so this is this value right here, and that's just that x value, right? My triangle is right there, and I just did 4.5 minus 3.4, so I got 1.1. It's that x value. And then we can do, let's see, we can do sine of 40 degrees equals 1.1 opposite over hypotenuse, right? And then we can rearrange that and say that length equals 1.1 meter over sine 40. And then that will, if you put that in the calculator, you get that the length is 1.71 meters if you round. So now we got the length. Now we plug that into our area. So we got 1.71 meters times the width, which is given 0.8 meters. And then if you plug that in, you'll get that equals 1.369 meters squared. Probably could have spaced it out better, but that's alright. So now we know all our variables for find the pressure or force. So let's go ahead and plug those in. Specific weight of water. I'm going to go ahead and convert this. This is what I was getting in the test. I'm going to multiply by 1,000 and get newtons per meter cubed. So 9, 8, 10 newtons per meter cubed. And then the height, 3.95 meters. Area, 1.369. Okay, and then you will get that, put that in the calculator, you get that the pressure force is 53.05 kilonewtons. So when you put this in that calculator, you will get it in newtons, and then I divide it by 1,000, and I got 53.05 kilonewtons. So this is important to the first step. So I'm going to box this. This is not the answer, but I'm going to box it because we're going to be using it later. Next step is to locate the center of pressure on the gate. So let's do that. To find and locate the center of pressure, we have, this is a formula we're going to have to use. So it says slant distance of this for the center of pressure. And remember that slant distance is, so if you continued at this angle and to the surface of water, so this is the surface of water, and this is the slant distance, right? So it's saying that this distance, we're finding this slant distance at this 40-degree angle to that center of pressure. So that's what that is. Equals the slant distance from the centroid, so not the center of pressure, from the centroid, plus the moment area of inertia of the gate, multiplied by the area of the, or divided by the area of the gate times the slant distance again from the centroid. So we're given the formula for this, right? It's right here. And then, so we need, and we already solved for the area of the gate, and now we need to solve for the slant distance from the centroid. So let's do that first. To do that, we're gonna have to draw a triangle again. So we got slant distance, then we got 40 degrees, right? And then we know that this value is 3.95 meters, right? So 3.95 meters, that makes sense because of this is the same, if you realize, it's the height from the centroid, right? So if we draw this triangle, we're drawing this, like, imagine we're drawing this big one right here. This is what we're drawing. We're kind of drawing this big triangle. This is our slant distance, this dotted line, to the centroid. And then we know that height, we already found it from the surface of the water to the centroid is 3.4595? 3.95. Yeah. Better, right? 3.95. And then we have that 40-degree angle here. So, again, use sine 40 equals opposite over hypotenuse. Rearrange that. Slant distance from the centroid equals 3.95 meters over sine 40. Put that in the calculator. You'll get that the slant distance, if you round it, is about 6.145 meters. That's a 4. I need to work on that. Okay, so we found that. Now we gotta find the area moment of inertia. So then we're given the formula. The B and H stands for base times height cubed. Our base will be that width, and then our height is 1.71 meters. It is 1.71 meters because it's it's the same value as this, which is from, it's just this height, right? So we're just trying to find the height of the gate, and we already found it earlier. Or we're trying to find the length of the gate, sorry. And we found that earlier. We found the length of the gate is L, so that's what that is. It's kind of weird when you say like base times height. You gotta think about it. It's really just the length. Okay, so you plug that in. So we get and that equals, put in the calculator, 0.3341 meters to the fourth. So we have all our values. Let's go to plug that in to find our slant distance to the center of pressure. Found the area we get earlier, 1.369, and then slant distance, plug that in, you get that the center of pressure slant distance is 6.1848 meters. Okay, now we're on the last step, and well, I think we have room. Let's do a little separation thing. So we gotta find the moment about the hinge. To do that, we need to draw an FBD, free body diagram. So let's go ahead and draw this. So I'm going to be drawing an FBD of the gate. So this is our gate. You know, I'm going to flip it around. This is our gate, an enlarged version of the gate. This is the value we're trying to find, that force. Our hinge is up here. And then we have our centroid in the middle. And then a little bit below it, we will have our center of pressure. And then we will have our pressure force acting on it. I'm going to give us some more room here. I'm going to draw the arrow down there. Same thing. Now we need to label some of these lengths. The dotted line, so just ignore that. It's just for help. So we know that the height is 1.1 meters. That was just 4.5 meters minus 3.4 to get that x value, that height right there. And then we know that, oh, we need to calculate that real quick. So we need to find the distance between the centroid and the center of pressure, and to do that we will do, so we need to find, we need to find the, we just need to find the difference between those two. If you do that, it is that 6.1848, right, meters minus, these are just values we've already found. I probably should have put it the other way. Now we're going to get a negative number. So once we get the negative number, just ignore it. If you do the other, I should have done it the other way. You'll get a very small value of 0.0394 meters, right? So we know that distance. We'll just call this, we'll call this x, or we already use x. We'll call this Q. For some reason we are going to call that Q. So we know Q. And then to do this moment, we're going to need to know this distance, right? Because we got to find, we're taking the moment about the hinge. So we need to know the perpendicular distance. So perpendicular of this directly upright force is going to be this distance right here. We'll call that A. And then we're going to need to know the perpendicular distance from this pressure force, which is just, the perpendicular distance will be this. And we'll call this B. So we got to find those distances. To do that, we got to do some more trigonometry, I believe. So, oh, and I'm going to put this angle in. This is 40 degrees, right? Yeah. So, to find A, we can do, and then we know this is 1.1. So we can do, you can use tangent here, I believe, yeah. So tan 40 degrees equals opposite over adjacent. So that can be this. And then you'll get that the A is a distance of 1.3109 meters. So to find the B value, which is the length of the gate from the hinge to the center of pressure, we have to find this length right here, right? So we already found the distance between the center of pressure and the centroid, so all we needed to find is the distance from this hinge to the centroid, which is good because we know that at the centroid it's just half of the height because it's a rectangle. So we know that that height is just half of the regular height because it's at the centroid, so 0.55 meters. And this isn't B, we'll call this, geez, I'm running out of there, so we'll call it C. And then we know that B is equal to C plus Q. Okay, and then we know this is still 40 degrees. So using our trigonometry, we can just say that C is equal to 0.55 meters over sine 40. I skipped some steps, but and then you'll get, well, actually put that in your calculator if you want to, but I know once you do that and then add it to Q, so we got, plug that in, plus Q, which is this number, we get that B length value is 0.895, about. Okay, so we found those perpendicular distances, so now we're ready to take our moment about the hinge. We'll say that clockwise is positive. So force pushing up, that's moving this way, which is counterclockwise, so it's positive. So let's say that the force times the perpendicular distance, A, so that's one moment, and then this is going this way, which that is clockwise, so that's negative the pressure force times the perpendicular distance of B equals 0. Okay, so rearrange this, we're trying to find F, right? So we get F equals pressure force times B over A. We'll go ahead and fill these in because we know everything. What did we say the pressure force was? We said it was 53.05 kilonewtons. The perpendicular distance to that is B, which is 0.895. All over the perpendicular distance of A. So the perpendicular distance is A to the force, the F value. So that was 1.3109. Put that in your calculator, you'll get that F is equal to 36.23 kilonewtons. So at a minimum, this is the force required to open the gate with the weight. We notice we didn't use the weight because it said not to. If it didn't say not to neglect weight, we would actually have force of weight here, and then we would have to use this perpendicular distance here, but we didn't have to do that, so this is the answer. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.